So today we are going to consider the third type of the ensemble we were considering, and that is boosting. So we've taken ourselves through ensemble principle generally, why ensemble could be very, very promising and could be what you need to actually get the job done, especially when you might have tried simple model. Of course, we should always remember that it's always good. The principle of machine learning is let the data speak. You don't just start directly from ensemble, but rather, so you start from simple methods and trying to see if you can get better results. And you keep going to higher, more complicated methods until you find out that, okay, maybe none of the individual models could really perform the expected accurate prediction. Then finally, we can move to boosting. We can move to ensemble generally, of which boosting is one of them. So we have discussed the general voting, and also we discussed bagging last week. So today we're going to look into boosting as one of the ensemble techniques, after which finally we are going to look into the stacking, which is one of the recent area that has been investigated mostly. So what is boosting? So from the name, as we can see it, boosting, now we are in we're in the COVID era. So after first dose, second dose, now we can be hearing booster dose. So something to reinforce what has already been taken. So it's an English word, to boost something. You can boost the performance. You want something to be enhanced. So that is linguistically. So, however, in machine learning, boosting could be viewed as an analogy. Let's say you want to consult several doctors, and based on a combination of their weighted diagnosis, so we can decide which one is better. So in boosting, we are not just voting randomly. No, we are going to look into the accuracy of the classifiers before we decide your own weight. So we don't vote at random. So boosting pay more attention to that. So the weight are usually assigned based on the previous diagnosis accuracy. So if we consult like 3 medical doctors to diagnose a particular disease, and we find out that one of them is a professor of medicine with several years of experience. So in that case, we cannot just give him one vote when it comes to the voting stage, when you want to combine the result of different medical doctors. But rather, I think common sense demands that we give this man a kind of a more weight. Maybe it's okay as a professor, with not just a professor, but a renowned professor that is highly trusted, who has maybe never made any mistake, or maybe very rarely made mistake when it comes to diagnosis. We can give him maybe 3. So a single vote from him is like 3. While if you are a resident doctor or a little bit also senior doctor, but not a professor of medicine, maybe we'll give you 2, while the new doctor could be given 1. So this will be determined based on their previous record of accuracy. So someone could be a professor of medicine, but maybe due to his own maybe kind of personality, the system doesn't trust him, or maybe he makes lots of mistakes. So in that case, he might not be able to get the same weight like another professor, colleagues of his will get. So in essence, what we are saying in boosting, you're going to do the voting according to the accuracy of each classifier. So the more accurate you are as a classifier, the higher the number of weight that's going to be assigned to you during the voting process. So, of course, something comes to mind immediately. So it means today somebody is always accurate, but it doesn't mean he cannot make mistake. So maybe whenever he makes any mistake, we are also going to multiply his mistake by 3, because we didn't know when he's going to make mistake. So this is one of the challenges also we are going to have with boosting. It looks very good, but then it can run into trouble. So, and that is why one of the favorite methods from my own experience is the stacking, which is going to be the last method we are going to consider, we see how that one is able to avoid this kind of possible pitfall of boosting. Another thing is the boosting algorithm can also be extended for the prediction of continuous values. That is, you can also use it for regression problem solving. You want to predict actual values, not yes or no or multi-class problem, which is called classification. So we can also use boosting for regression problem. So compare with bagging. So it is based on experiences often established that boosting tends to achieve greater accuracy. Of course, there's a risk of overfitting the model to the misclassified data. As you are going to see the principle, the way it works is it can expose it to being overfitted to certain samples that have been misclassified before. Although quite very successful, the disadvantage of the original boosting method is that it requires very large training sets, straight training samples to be able to achieve reasonable results. So when you are faced with very few data samples of data, it might not be a good option to check, although several variants are coming up of recent. Now, how do boosting, how does it work? You see, the idea of boosting, just to summarize for us, is a the idea of boosting, I hope you can see my writing, yeah. Let's say we want to train three classifiers and then combine them in a boosting setting. So we have classifier one, we have the samples are here, this is sample data. So we train classifier one, the first classifier, number one. We train it on this sample. Then we check the accuracy. Pay attention. We check the accuracy. You take note of the misclassified samples. We need the misclassified sample. This is why boosting is totally different from what we are used to. You have to take note of the misclassified sample. Take note, identify them. Identify the misclassified samples. And what do we want to use it for? In the next stage, those misclassified samples will be given more probability, more weight of being resampled. So that if there's a sample, maybe sample number 3 has been misclassified here, we give it a very high weight in such a way that in the next available sample we are going to use for our training, the next classifier, we make sure that this number 3 is repeated several times. Because the idea is that we want the next classifier to pay more attention to those samples that have been misclassified. It means those data, they are not cooperating with our classifier. So we want the next classifier to focus more attention on them and get them classified correctly at all costs. This is the idea of boosting. So that if after this stage, this one was now gotten correctly, then we identify what are the mistakes this one is making. This is classifier 2 now, number 2. We identify those mistakes. We give those mistakes more weight so that they'll be repeated. Maybe number 5 now is not correctly classified. Sample number 5 will be repeated several times, a couple of times, depending on the weight. And the next sample to be used for training classifier 3. So you can see that boosting it proceeds in series. You cannot go to the next, you can't train the next classifier until you are finished with the first one. And this is a major problem of boosting, slow down the process. Unlike in bagging, whereby you can even distribute the task among yourself. You go build 3, you build 3, you build 3, then we come back together and combine our results. But no, in boosting, no, we have to finish one, identify the misclassified samples before we can build the next classifier. And that continues until no matter the number of classifiers you want to build. Now, therefore, we say in boosting, learners are learned sequentially. This is the big difference, sequentially. So with early learners fitting simple models. Let's pay attention. The early learners, they fix simple models to the data, and then they analyze the data for error. That's what I just explained here. They check the outcome of the classification model. What are the mistakes we made? So the next models are going to be made to pay special attention to those samples that have been misclassified in the previous stage. So therefore, it means that the goal is to always improve the accuracy from the prior model. So you want to increase the accuracy of the next model considering the previous model. If the previous model is trying or achieve like maybe 70% accuracy, we target those mistaken samples and then put everything together, increase the number of times we repeat those mistaken samples, and then try to build a new classifier that will be better than the previous one. Now, so, and like I said, to do that, we achieve that by ensuring that when an input, which I call sample, input, or we call it sample, when an input is misclassified by an hypothesis, by a hypothesis, so the weight of such input is increased so that the next hypothesis is more likely to classify it correctly. This is what I've explained here. See, we have sample number 3 here that has been misclassified. The model we built here, model 1, was unable to classify this sample. In the next model we want to build, we make sure that we repeat this sample 3 multiple times, so that this classifier we are training now with this data will be made indirectly or directly to pay more attention to this, because this is being repeated. So hopefully we want this one to be better than the previous one. And then the same thing continues until we get to a convergence, or we specify the number of iterations we want to try out. Now, so that here we have an hypothesis function 1. It made some mistake on this. So hypothesis function 2, we want to make sure that this hypothesis function 2 is more likely to classify this one correctly. It might make another mistake. We will focus on its own mistake and let the next model to pay attention to the mistake of this H2. And then H3 also will have solved the problem of H2. Then H3 might make its own mistake, We make the next model to be trained, H4, to pay attention to the mistake of H3. And then it continues like that until we have a convergence or we satisfy the number of iterations we set up. So we summarize the fact that the idea of boosting converts weak learners into better performing models. This is the idea. So it's try to see that, okay, ordinarily simple models could be made to become very powerful model by way of trying to let it pay attention to those samples that have been misclassified before by repeating the number of times it occurs. Now let's look at an example visually. Suppose there are just 5 training examples. We have 5 training examples to make it easier. These are the training examples. We have sample 1. We want to predict somebody is diabetes or not. So we have sample number 1, sample 2, sample 3, sample 4, and sample number 5. And remember that this one, they have their own attributes: name, age, blood sugar, history of the father, history of the mother, maybe any of them is diabetes. So many questions. So these are the attributes. So this is known as sample. When we are make mention of sample, I'm talking of the row now, the row. So this will contain all the information provided, all the information. Now, suppose that we have only 5 training examples to use in building our boosting ensemble. Now, initially, each example has 0.2 probability of being sampled. You know, when you do a sample, when you do sampling, so they have equal probability, because probability of picking any one of them is 1/5, because random sampling. So which is now. So in the first round of boosting samples with replacement, of course, there's with replacement. So in the first round of resampling, we resample our data with replacement. So we had this. This was the first one we selected. It also used resampling method. So we selected sample number 2, sample number 4, sample number 4, 3, and 2. You can see that 4 has been repeated because they are at the beginning, this is the first time. They all have equal probability of being selected. And once you select one, you return it back. So that is why it is possible to select it again. We call it sampling with replacement. Now, so we take this and then we build a classifier from it. So build the first classifier, which I'm going to call H1. H1. This is classifier number 1, or model 1, or hypothesis function 1. Called model 1. Now, then we analyze it. Once you build model 1, you analyze it. Suppose now that example 2, 3, and 5, samples 2, 3, and 5 are correctly classified. See, assuming that sample 2, 3 are correctly predicted by the classifier. Now, by the classifier, there was no mistake. And then sample 1 and 4, for example, are wrongly predicted. Sample 1 and 4 are wrongly predicted. Just let's assume. So now we are going to make the next model. We want to train model 2, H2, to pay attention to these examples that have been misclassified. They have been wrongly predicted. It means the model we have generated did not understand these 2 samples very well. So what we do next, before we build our next model, is that we need to increase the weight of this sample 1. We need to increase the weight of this sample 1 and sample 4. We need to increase the weight of this sample 1 and sample 4. Now, so it means increasing the weight means the possibility of selecting 1 and 4, sample number 1 and sample number 4, should be more. So in which case, this is going to make it very easy, hopefully, for the next algorithm to focus, to pay more attention to those that have been misclassified. Whereas the samples 2, 3, and 5 that have been correctly classified, you decrease the weight. We don't want them to be repeated in the resampling process. See? So we increase the weight of those mistaken samples because we want our model to concentrate more on them. So that if you can repeat it maybe 3, 4, 5 times each of them, why those that have been correctly classified, because it means this model is already taking care of them. H1 has taken care of some. So let's make this H2 to focus on those ones that have not been taken care of by this. So by so doing, this one hopefully will be able to solve that problem. So the second round of boosting sample, again, 5 examples, but now example 1 and 4 are more likely to be sampled. You can see now. So when we want to train this one now, which is the second round of the boosting process, so 1 and 4 samples are most likely going to get selected several times. So in that case, this one can pay more attention to it. So when I train H2, paying attention to 1 and 4, then again, we check the accuracy of it. Where is the mistake? So where is the mistake coming? We are going to look at it again. Where is this mistake coming? Is that maybe sample 3, maybe it's only sample 3. So in the next stage, we are going to increase the weight of sample 3 while reducing the weight of others that have been correctly classified. And so on until some convergence is achieved or the number of iterations you set is reached. So we keep trying to focus on those samples that have been mistakenly classified. This is an example of how boosting works. Now the steps could be summarized thus. Starting point weights are assigned to each training tuple, a training sample. So a series of K classifiers is iteratively learned. So you train them. After a classifier MI is learned, the weights are updated to allow the subsequent classifier MI plus 1 to pay more attention to the training set that were misclassified by MI. So those that H1 made mistake on, H2 should pay attention to those. Those mistake of H2, H3 should pay attention to the mistake. The mistake of H3, H4 should pay attention to it. And it continues until finally, either you set up a particular sorting criteria. So that the final M star, which is the combination, which is to now you need to combine now. Now we have H1, H2, H3, H4 now. They need to vote now. They need to vote. So to generate the big model, we call it M star. This is the big model we want to generate now, the final ensemble. So it combines the vote of each individual classifier, where the weight of each classifier vote is a function of its accuracy. Now let's pay attention to this without getting confused. We were talking of weight before. That was weight on the resampling of the data, because the data will be resampled at every point, anytime you want to train the next classifier. So that was the weight we were talking about before. But now when you want to combine, we don't use majority voting here. Everybody have the same vote. No, we look at the accuracy of these. This one actually achieved 75% accuracy. This one got 85%. Because hopefully improvement kept coming. This one got 95% accuracy. This one got 93 or something like that, or 95. So we give more votes to those one with higher accuracy. This one vote is going to be 2. This one is going to be 2 because of this one is going to be maybe 1, and this is going to be 1. So we give more weight to the vote of classifiers with more accuracy. This is why we are going to take the final voting, so that if this one said, okay, this is yes, and these 2 guys said no, because they have 2, that's going to be 4 against 2. You see, we have such a situation. That is the kind of voting that boosting made use of. Diagrammatically, we can visualize it this way. See, this is iteration 1, this is iteration 2, this is iteration 3. So the final classifier hopefully will be stronger than the individual. But however, know that before you build this one, you have to finish this. Before you build this, you finish this before you build this. Now, if you allow it to be built simultaneously, then you are talking of bagging. In that case, you are talking of bagging. If you build this one without considering this, you build this without considering this. So everybody, this one is independent of this one is independent of this, then what you have done is bagging, and then you can do the final combination, which is a possibility. Yeah. However, with boosting, so now this one will give you a very clearer visualization. This is the data we have. This is our training data. Now, when you develop sample 1, this is why I say it is sequential. When you develop, this is the first sample, a resampling. At the first resampling, all the samples, they have equal probability of being selected. Yeah, because we have never trained anything on them. We don't know which of the samples will be good or will be very easy to classify or will be difficult to classify, because samples are different. Some patients are very difficult to diagnose. Medical doctors knows that. Some patients may have seen them. May have seen some patient, you can easily tell what kind of disease the patient is suffering from. Meanwhile, some patient, after running several tests, you still not be able to identify them. We have this kind of thing in our data set. So in similar way. So once you run the first system through, you can easily see that, okay, this is sample 1. So all of them, they have equal chance of being selected, since there's nothing that points that a particular sample is difficult or not. Now, so in this sample, all of them, they are equally probable to be selected. So this is sample. Now you run the model, you develop the first model. When you develop model 1, then you have to check the accuracy, and check the error. So those samples that this model was unable to classify correctly, you make sure that you give them more weight so that they are repeated when you are going to generate sample 2 for training another model. And that continues. So it means if I don't finish with model 1, I cannot develop model 2. If I don't finish with model 2, I cannot develop model 3. And developing model 3 would depend on the outcome of model 2. You can see that is why they are linked together. And that's what we call sequential development pattern. And that's why it's going to be time consuming. It makes it very difficult for people to collaborate to develop boosting ensemble, because I need to see the outcome of one model before I can develop the next model. So in that case, go and develop 20, develop 40, then we can bring all of them together. No, it doesn't work for boosting. It can work for bagging and the direct voting method that we've discussed earlier. So this one is done in sequential, so order. So the hope is that by the time you keep doing this, letting this focus on the most difficult one, at the end of the day, you might going to have the final model K, which is the last one. K can be 10. Maybe you want to go for 10 iteration. So in that case, we're going to have the final model. Then we now combine all this model 1, 2, 3, up to 10. We don't just combine them by majority voting, as I mentioned earlier, but rather you have to look at the accuracy of each of the model and assign higher weight to those models that are more accurate compared to those models that are less accurate. So this is how boosting works. And I hope that is clear to everybody. Now, so summarizing it, boosting, we said, when you look at it from the partitioning of the data, as I've explained, so you give higher votes to misclassified samples, which means it's going to start in the second phase. Because at the first phase, when you want to develop H1, the false hypothesis function, you don't have any information about the samples, which sample will be misclassified or not. So that is why the first model you are going to build in the boosting ensemble system, you need to, all the samples will be equally probable to be selected. They have equal probability. However, immediately after the first model is built, you check the accuracy of that model. Then the subsequent one, when we go for the H2, then we look at the misclassified samples. Samples that have been misclassified will be given more importance now, so that we repeat it in the resampling, so that H2 can pay more attention to them. Because if H2 has, maybe there's a sample called sample number 2 and sample number 3, if we pay more attention to this, if we pay more attention to this one, if H1, H2, and H3 pay more attention to this, at least the possibility of, because it's giving it more importance. What are in this patient that is making it difficult for me to be able to identify them, to be able to diagnose this patient? Why are they difficult? So when you pay more attention to that patient, you might be able to see some of the attributes that you were missing. So this is the idea. So this one will pay more attention to those mistakes, of course, in addition to all other data that have been provided. Not only this, but this one will be repeated more times. This is the idea. So you give higher vote to misclassified samples. That is, you increase, what my higher vote is, increase the probability of selecting them. Increase the probability of selecting the misclassified samples. I hope it makes sense to us, because someone once said, why are we paying attention to those bad samples? Because we want to make the model to identify them at all cost. Either the sample likes it or not, we want to get them correctly classified. That's the idea. So, because those ones that were classified correctly, easily, most likely they're very clean data. They're data without problem. There are samples that are very fantastically correct. But then we have some samples that are not very clear. So the next subsequent models are made to focus on them and pay more attention, and by so doing, they get them right. The goal is that we want to increase the accuracy while reducing the bias. So we want to increase the accuracy while reducing the bias of the algorithm, of the model developed. And then they use the principle called the gradient descent. And then the function to combine them is I mentioned this one, is weighted majority votes. It's not it's not the majority, it's not just direct majority carry the vote, but weighted majority. So you give weight to the model with higher accuracy, so that they can take advantage of that. And there are several examples of this kind of ensemble, very popular in literature. So we have the Hader boost, we have the stochastic gradient boosting, we have GBM, the hex GBM, the light GBM. So many variants of boosting algorithms have been proposed in literature. So summarily, we can say the advantages of boosting include reducing the bias, very simple to implement, fairly good generalization. That is, good generalization means we can hopefully get better results, and also, of course, increase accuracy, while prior error needs to be known ahead of time. So people see this as an advantage of it, that, okay, you have the idea of how prior error needs to be known. That is, you have an idea of how the previous model is behaving or has behaved, so that you can give you some kind of hint on how to develop the next model. Unlike the case of bagging and other method, here everything goes in parallel. I don't have an idea of how your model is performing. I don't have an idea, you don't have an idea about how my own is performing. We train several of them in parallel, then we combine the result. But in this case now, we have information about the first model. That information will assist us to train the next model to focus on the mistaken samples. So by so doing, hopefully no samples will be left undetected. So it means our models will be able to have characteristics of all samples in the training set. So when the new testing set is coming, hopefully our ensemble will be able to develop, will be able to predict better than even bagging or any other methods. Because the idea is that when you train in bagging, you train all the models in parallel. It means there could be one or two samples that all the models made mistake in classifying them. There's a particular sample, number 3, number 4, that all the 21 models we train, they all made mistake in that particular sample. But boosting will not allow that to happen. Boosting will make sure that the next model pay more attention to those difficult samples to classify. So at the end of the day, almost all samples will have been correctly classified in the training set. So when you have testing set, it means you have a model that has understood everything that could come from the data. And hopefully you can get better results. So this is just the secret behind boosting. But however, the challenge is there. So the cons includes there's probability it can overfit in presence of noise. This is the challenge. There's possibility of making, because now we are focusing more, if the data that is being misclassified is a noisy data. Let's pay attention to this. Let me draw something for us. You see, when you are dealing with data, it is assumed that, okay, your data set are here. But there are some data set here. These are called outlier, or very noisy data. So these samples are misclassified. Ordinarily, we don't care about them in normal system. If we know them, we can kick them out of our data set. But however, in boosting, since boosting always makes the system to focus on misclassified data, we don't try to check what is the source of that misclassification. Is it that the sample is a noise? Is it that the sample is an outlier? If it doesn't pay attention to that, you might end up forcing your model to go and learn this out of bound. These are out of space data. These are outlier. So you are forcing your model. Why try to understand outlier? They might end up missing some of the correct data here. This is the challenge that could come. So if there is a noise that could be overfitting, you might be forcing your model to overfit into the noisy data. This is why we usually encourage people to do what we call pre-processing before you start boosting modeling, so that you are sure that any noisy data or outlier is already removed from the data. So you know that, okay, you are dealing with data that follow the usual characteristics of the data that is expected. Now, so one challenge that could come from it is it could overfit in presence of noise. Of course, it requires careful tuning of different hyperparameters, because every time you train the next model, because the data set now is a little bit focusing on different sample more than the other, you have to do hyperparameter checking always. Then the further it is serial implementation, it supports serial implementation. That is, one model must finish before you go to the next model. Imagine if I want to train 165 model. You can imagine how long it's going to take me before I do that. So it takes a lot of time. It is time consuming. That is the problem with this kind of ensemble. Now, finally, towards the end of the class, we are going to mention, look at the two of them side by side. So bagging and boosting. So here, you see every item has the same probability to appear in a new data set. That is bagging. So when you resample, the two of them use resampling, that's fine. But however, in boosting, the samples are weighted, so some of them will occur more often. So after the first one that is designed with equal probability, starting from the next one, the H2, the second model, it will be reweighted. The weight of the samples will be different depending on why they give more weight to the misclassified samples. So that is boosting. So in bagging, you have parallel training stage, while this one build learners in sequential way. So which means this is going to be time consuming. So that is why we don't, if you need real time, that is why boosting is not recommended in a real-time application. Real-time application is where you want your algorithm to predict, you want your model to give you result as the event is taking place. Few seconds lateness is not allowed. So boosting is not for you, not that kind of thing. Rather, you go for maybe bagging or another one we are going to discuss later, stacking. Now, final decision is the average of the n learners, whereas final decision is weighted average of the n learners. So because beta classifiers have higher weights. So if you have 95% accuracy, you have more weight compared to another one with 65%. You see? So like bagging, where we give everybody the same thing. Now, so this bagging work on reducing variance and hopefully solve overfitting problem, whereas boosting reduces bias but increases overfitting a little bit. So I told you before, variance and bias, they are always working on opposite side. You can hardly get a system that can solve the two problems. Because as you are solving bias on the number line I gave us that time, one is on this one side, another one is on the other side. We are moving towards this side, you are closing, you are moving back here, you are closing here. So you have to try to be in between as much as possible. However, bagging is more likely to solve problem of reduce, it can reduce variance, while what can reduce bias. So the idea is, okay, can we have an hybrid system where we try to bring the two of them together in a single system and try to see how we can benefit from it. These are new thinking areas. Can we have several bagging coming up to participate in boosting? So possibilities are not limited. It's just a matter of the kind of our minds, how much we can think and try to see how we can improve our situation using the ensemble systems. So this is the pictorially, we can see here to the right. This is bagging. This is bagging. You see, it's in parallel. Your training is in parallel. Training is in parallel. And then this is boosting. You can see here, sequential. So your data goes, you build a model, you analyze the model, then you create another data by increasing the weight of those misclassified sample here. You can generate a new sample here. You can see now that this data, that's only one here, it has become two here. So you now build another model. Then you look into the model again, analyze it, get those misclassified samples, use it to create, use those feedback to create a new resampling, resampling data set, and then try to use it to build model. And this continues until you reach the number of iterations you set up, or you set up a particular parameter that, okay, once we get to some number of accuracy for the last model, we can stop it or whatever. So this is possible. This is on the bagging and boosting. So now we're going to have a look at the way boosting works. Now, I think it's a good place to keep it for the day. Now I'm going to show you an example from Weka on how can you run a boosting algorithm in the Weka environment. And I know a question will come to people's mind, which one is better? Is it bagging or boosting? Like I said, the principle of let the data speak should always guide our way. We should never forget it. It's a very big principle in machine learning. Let the data speak. Always remember, because the data you have will determine which one will be better for you. If anybody just tells you that boosting is better in all situations, no. He or she doesn't understand how machine learning works. So let the data speak. And like I said, don't just start from boosting, start from simple models. If those simple models are able to solve your problem, you don't need to waste your time on all these very long processes. But sometimes we might get stuck. That you try all possible single models, you never get it right. Why not then start the ensemble, start from the one that is easier for you, and then continue to the complicated one. So this is the principle that is highly recommended in machine learning, and we should never forget that. So this is of course, as usual, go through the Explorer. So hopefully later I'm going to show us how we can use the experimenter. We are going to discuss that one later, inshallah. So for now, we are in the experimenter, in the Explorer. As usual, we're going to load our data, get our data in. So our usual data we are using, program file, the diabetes data is located in the Weka file, data, diabetes data. Okay, now you have loaded the data. So you go to classify. After checking that, okay, this is what we want to predict. So you go in here, you go to meta. Inside the meta, you can see several ones. You can see the first one, Ada Boost. You see, Ada Boost is one of the foremost boosting ensemble that was developed. So we have other methods that some of them are not yet added here, like XGBoost, and so many other methods of boosting. That's why you can go in your own ensemble, you can go into tools, you launch your package manager, and just once you launch the package manager, you search for boost. You will see several boosting algorithms that will be displayed for you. Then you can install it to your Weka if it is missing in yours. But here I have here with me Ada Boost. So you click Ada Boost. So Ada Boost is there. Click it as usual. It's already set for you. So you need here, you select, this is the classifier. This is the parameter you need to set. You need to set the classifier you want to use. So you have to set the classifier. So select whatever you want. You have, in those days used to be, they were all built for decision tree, originally built for decision tree. So that's why you see the default is all about tree. But the fact is you can use any method for them. You can actually use any method. So you want to use our IBK, k-nearest neighbor, or you want to use any method you want. And then this iteration, you have to set it how many times, the number of iterations you want it to repeat. So I want it to generate how many models. So it should run 10 times. So it's going to run the first one, check the result. The next resample is going to resample your data. That is why you have the weight threshold. To keep recycling the data until each of them keep improving over the other. So if you like, you can change the classifier. You want to use 3, you want to use 48. I want it to run 5 times. I just only have 5. So it depends. So this is how you use boosting ensemble in the Weka environment. Like I said, if you want to add more, there are so many of them there. You open your package and then search for Boost. Then you see anything that has to do with boosting that has just been uploaded to Weka online package, which will be downloaded for you in your system. So I think this is how we are going to have it for the day. So Barakalafik. So, and then if there's any question, we can welcome 1 or 2 questions before we call it a day. Thank you very much. Okay. Mr. Bolaji. Wa alaikum salam. Mr. Bolaji raised up his hand. Let's keep him the audience.
Assalamu alaikum.
Wa alaikum salam. Okay. Go ahead with your question.
Okay. Yeah, my question is with regards to the boosting that you just talked about. I want to ask, is boosting a homogeneous ensemble? Because I noticed that the example you gave, you only use one classifier. It's just that we are now, checking. So is it that it's a homogeneous ensemble system, or can it also be heterogeneous as well?
Yeah, based on the present system that Weka Explorer support, it is homogeneous. Originally, it is homogeneous. Yeah. So because you give the data, it keeps resampling the data while paying attention to the misclassified data, and then retraining the same model. Of course, it could change the parameter of the model. It could try to see if the model is better at this point or the other. But yes, it's an homogeneous ensemble. But actually, it is possible to be extended to heterogeneous. But originally, it is homogeneous. Because when you are resampling data, checking these, and also you want to see, okay, how the same model, that's why they say it improved the same weak model. That's a k-nearest neighbor. When you make it to focus more on misclassified sample by itself, next time it's focusing more, you want to see how it's going to behave when it sees it sees the same sample in a repeated format. So homogeneous is homogeneous ensemble, but actually if it is in a programming environment, we can try with several things, but then the complication with setting, because it means every time you want to change, you are resampling and increasing the weight. At the same time, you are changing the model. You do like 2 things at the same time. So it brings complication to that. But then, like I said, the good thing about ensemble is homogeneous can be made to be heterogeneous. Like I said, this kind of thing used to be done for decision tree in the past, tree modeling, but today you can use any model for it. But it is better at the beginning to make it homogeneous. Of course, presently the Weka won't support that homogeneous. So you put that particular one there and then it run it as we have explained. But however, it is possible to make it to be heterogeneous, but then that is going to incur some computational, of course, complexity, and you have to do the tweaking manually by yourself. I hope that is clear.
Okay, yeah, it's okay.
Okay.
Thank you, sir.